So the topic probably is a little different from the other that you see in the section. And I'm only going to mention precision homology towards the end, like I will get there. But really, this journey, understanding learning on graphs, really started the last 3 years ago when I was trying to see how geometric topological ideas can be better integrated into helpful solution learning applications. Okay, so I hope that this, by telling you a little bit about my journey in the past 3 years, this is an extremely rich field with a lot of open problems, especially in terms of circuit understanding. So hopefully that's also useful for you. All right, so as I said, this is about analyzing graphs. Now, I assume that I really need to motivate why we're interested in graphs. This is a very versatile type of data that can be modeled just both geometric data and also exponential graphs. There are many important tasks that I would like to do with graphs. It can be, trying to compare graphs, it can be trying to do prediction using graphs, and so on. And in the past decades or so, there's a range of there are several families of different graph neural networks that have emerged to help us to perform learning on graph in a data-driven manner. Okay? And this has already been used in many applications. But despite such a great, tremendous advancements, there are still a lot of limitations, and especially in terms of what's their capacity, what can they do. And as I said, this is really about some of my recent exploration on the both understanding and using graph neural networks. So there's talk a lot of this, and I'm going to spend some time to give you a brief introduction to two very important families of graph neural networks, the so-called massive passing graph neural networks, and also the so-called graph transformer-based architectures. Okay? And most of the talk is going to focus on one type of theoretical question on the graph neural network, namely its representation power. Okay, so that's the middle part. And towards the end of the time, I would also tell you a bit about from the practical aspect, how do we mitigate some of these limitations that graph neural networks have. It's there, some topological and spectral ideas for use. Okay. And you should feel free just to interrupt me anytime you have questions for clarifications. All right, so first, some introduction to popular families of graph neural networks. So when we talk about neural networks, mathematically, we only can think this is a neural network is a way for us to parameterize a function from an input space to an output space. Okay? And when we design neural networks, really, what is the precise architecture depends on the type of data, the type of maps you're trying to approximate. So for example, so here, what I'm showing here, this is one of the simplest, sort of fully connected straightforward network. So this essentially is parameterizing a function going from R3, that's 3 input, to R2, output of 2 numbers. Okay, so in the middle, the parameter of all of this little circle, the so-called neurons, the parameter of them essentially give you the parameterization of your function. And during the training process, you basically adjust all those parameters and then find the best way so that fits your ultimate task, your loss, minimizing the loss, for example. Okay, so that's when we say training neural network. Essentially, we have this architecture, we're just trying to adjust to find the best parameters that optimize the function. Okay, so this is a very simple type of neural network that works for functions going from RD1 to RD2. Two Euclidean spaces for fixed dimensional input, output, fixed. Okay? Now, if your data has more structure, then often you can leverage that structure. So, for example, if your input is now an image, of course, you can view this as a high-dimensional vector, as a high-dimensional space. But the image also has spatial relations between pixels. Okay, so you can leverage this spatial relation and then try to design a different family of neural networks. So, for example, the most popular convolutional neural networks is actually also aggregate information based on the spatial locations. Okay, Okay, so this then you design CNN for images. All right, but now how about graph data? Well, this brings a lot of challenges because very fundamentally different from the earlier type of data. A graph in general, we don't have fixed number of nodes. You can give me a graph of any size. And even when we talk about fixed number of nodes in the graph, your connectivity, your combinatorial structure might be different. Okay, so the input is not even of fixed size. So now how do we kind of penetrate function? How can we have a small bounded complexity, bounded number of parameters to try to model a function? Okay, so in particular, we would like to have, in some sense, shareable parameters that should be independent to the combinatorial structure of the graph and to the number of nodes in the graph. Now, about a decade ago, we're starting to have quite a few different graph learning architecture emerging. Okay, so this is the idea behind one popular family called massive passing neural networks, MENN. So what does it do? Well, so the idea is actually very simple. Say that here we have the input graph, okay, of some size. What I'm going to do is that I'm going to focus on every node. So every node will have a feature vector associated with it. At the beginning, let's see that every node has a d0-dimensional feature associated with it. Okay, and as throughout each of them later, what you do is that you simply keep updating the node feature here. Okay, and this update, everyone, all the nodes will use the same update rule. Okay, so the node feature will go from, say, the d0-dimensional vector to a d1-dimensional and so on to a dimension. Okay, but everyone, all the nodes will share the same update rule, which means that I only need to parameterize this update. Okay, that independent of the size of the graph. Okay, and how do you exactly do this update? Well, so you have a feature here. So essentially, what you can think is that I want to take the combinatorial structure of the graph into account. So if I want to update the feature of this node at each iteration, what I'm going to do is that I'm first going to collect all the features from my neighbors. So this is how you take the graph combinatorial structure into the picture. I take all the features from neighbors. I first perform one function, this is a parameterizing function, to aggregate them. And then I use another function to update this aggregation together with the remote feature to get a new feature. Okay, so now the calculation of this update rule essentially is in these two functions. Okay, so this is usually implemented by the so-called MLP, multi-layer perception. What's the requirement is that this function, I'm taking a collection of all my neighbors' features. Okay, so when I aggregate, each node could have a different number of neighbors. So when I do this aggregation, I have to do this in a permutation invariant manner. So it shouldn't depend on the order of my neighbors. Okay, and that's basically the only requirement. Okay, so now during the training process, you have a specific way to set this up, and during the training process, you just keep optimizing the functions for this the parameters of these two functions till you get the best performance. All right, so here is just one simple example, one specific way to implement this aggregation. So here, the aggregation function is not even parameterized. I simply average all my neighbors' feature, and then after that, I perform a linear transformation of the aggregated feature. Then I do a nonlinear update. Okay, so this is one of the early graph neural network, and later both of these two functions become much more sophisticated. All right, so this is a very flexible and powerful architecture. And as I said earlier, it's already used in many application domains. And in fact, I mean, in the field of geometric deep learning, you would see that a lot of the handling in geometric deep learning, very often you handle geometric data, let's say point clouds. Okay, and the way that you handle those point clouds has a lot of similarities. Number one, given that point clouds, you could convert it into a geometric graph, which is take the skeleton of the Ribs complex, for example. Okay. Number over 2, when you handle the point clouds, it's like to have a set of points, and you want to handle this in a computation invariant manner. You want to be indifferent to the size, which is so much what you are placing in the graph. So you can think point cloud is order 1 tensor, and y is order 2 tensor. Okay. But at the same time, first, actually, different from the traditional architecture, like the standard feed-forward neural network or the CNN, the theoretical understanding for graph neural network is much more limited. Okay? The understanding is limited, and also it turned out that their power is also limited. So they have limited representation power, which I'll come to in a minute. Okay? And there are also many other things that they're not good at. For example, as you can see that this message passing, every node will keep aggregating information from my neighbor in each iteration. So you have a long path for the two endpoints to reach each other, the information to reach each other. Then you will have to aggregate many iterations before they can get the information. Okay, so not only that, later I'll point out there's a so-called overselection. And when the paths become very long, you also don't know what information is important, so it's harder to encode the information. Now, one reason that it is hard for you to aggregate long-range interaction is because that you are taking this, you only connect to your neighbors, and then you have to work along the paths in order to collect information between two nodes that's far away. Okay. So one way that people started that to help with this issue is to, instead of just only every time only take information from your neighbors, or by the way, look at information between any two parallel nodes. Okay, and this can be achieved using transformer-like architecture, where this information between any two nodes will be achieved by the self-attention. Okay, so what do I mean? So here is a very simple view of the transformer. So this is standard transformer, and now coming to graph case with you. Okay. So really, the error line, the core component of the transformer, essentially is basically a sequence-to-sequence permutation equivariant function. Get to that in a minute. So you can think that my input, for example, my input is a sequence of n points in RV. Okay, and then my output will be a sequence of n, same size, sequence of n points in different dimension. Okay, now a standard transformer architecture will consist of a collection of these transformer layers. Each of the transformer layer has the following simple structure. So each of this transformer layer would map the sequence of n points in RD to this sequence of n points in a different dimension. And the way it does that is that first, so this is my input sequence X. Okay, so you can ignore this too. So first, basically, I want to know that pairwise, how does point I affects point J? And that's simply done by looking at the similarity between the inner products. Okay, what I have here, this two matrix WG and WK, it's just you further transform your function hopefully to better feature space and then do the inner product. But the key idea is that first, I do pairwise inner product to get the so-called attention between nodes I and node J. Okay, now I know that how does node I influence node J through this inner product. I simply use that to weight all the points, the contribution of all the points to get a new value for the output. Okay, so that's it. So the key is this attention matrix. As you can see, that this attention matrix essentially is an n-binding matrix, just encode the influence of I to J. Okay, and this is done just through this inner product. The non-linear part is here, the sort of softmax, which has a normalization there. All right, and as I said, each of the transformer layer is basically sequence-to-sequence commutation equivariant fraction. What does it mean? That means that now, if you commute your input by some commutation, okay, Then your output is also sequenced, then the output will be commuted in the same way. Okay? And it's easy to see that this architecture satisfies this property. So this is just a transformer, but this has nothing to do with graph. So when we are given graphs, how do I put the graph structure into this transformer framework? Now, there are two ways that one can achieve this. Okay. The first one is so-called through the position encoding, and we are giving this absolute position encoding to differentiate with the next way that I'm going to tell you. Okay. So what is this? This is just saying that, okay, you give me this graph, and each of the nodes will be one of this input. Okay. For every graph node, I'm first going to summarize some information about its couplet, about its combinatorial structure at this node as a feature vector. Okay, so every node now is a feature vector, and I feed it to the input of graph transform. Okay, in other words, all the encoding of the graph structure lies in this node features. Okay, and once the node features are supplied, then the remainder of the graph transformer doesn't have any consideration of the graph structure. I'm just treating all of them equally, doing the attention and carry out the same process. Okay? And so that's the first way. And this is what I call the smooth position encoding framework. So for example, one popular way that people use to encode to give a node feature is essentially you take some sort of spectral operator, say Laplace in any version that you like, and then you take the eigenvectors and use those top k eigenvectors to do an eigenembedding. And this will embed every graph node into, say, three-dimensional space, and you use that as your initial node feature. Okay, this actually has issues when you have eigenfunctions with eigenvalues with multiplicity, which I touch upon later. Now, the second way is saying that, okay, maybe let me try to modify the attention itself, try to make it more respect to the graph structure. Okay, instead of just work on the input. What do I mean? So let's say that I'm giving you a matrix, which essentially, so a matrix D, which essentially just encodes some pairwise information into more nodes that also encode the graph structure. So example, this D could simply be the adjacency matrix of your graph. Okay, but you can also use other interesting object. You can have a graph shortest path distance, or you can have the matrix of effective resistance distance as your matrix D. Okay, so this D now encodes some information about your graph. Graph combinatorial structure. Now, the standard attention, just you do the inner product between features, and now you say that, okay, I'm also going to weight this attention using this matrix D you supplied. Okay, and how are you going to weight will be a learnable component. You'll parameterize this and then doing training. Same after you compute the attention matrix, you have another way to weight this before you use this to aggregate information, update your node feature. Okay, so the key is that the first way of smooth position encoding, which is called APE, is just encode everything at nodes and then supply it to transform. The second relative position encoding, which I call this RPE, is basically encode information into A and by a matrix D, like shortest path matrix, and then supply this into the transformer and weight this at every stage. All right. Now, these are the two most popular family of neural networks. And the first question we should ask is that what can it do? Okay, and how can I understand the capacity of this model? And there are different ways to approach this problem. So what I'm going to now talk about is in the field, people have been looking at so-called expressive power of these models through something called Weisfeiler-Lehmann tests. Okay, so what is Weisfeiler-Lehmann test? I'll call this WL test from now on. This is actually a graph isomorphism test. It attempts to solve the graph isomorphism. To give you two graphs, this is a test that will tell you either these two graphs are not isomorphic, or it is say that I couldn't tell. They may or may not be isomorphic. So they cannot completely solve the graph isomorphism, but if they can, it is known that they can differentiate most the pair of graphs that we cannot differentiate will be actually zero. Okay, so you can differentiate most pairs of graphs. And it's also a very efficient procedure. Okay, so how does it work? So it works as follows. This is the so-called one-dimensional order one bispiral test. You give me two input graph. And let's actually now view graphs attribute to the graph. Namely, every node will have some initial feature, okay, attributes. And if you given the graph without that, you can just take constant or take a degree as your initial feature. Okay. Let's say you give me this two attribute graph right now, the feature is just a degree. Okay. How do I compare to see whether they're the same or not? A simple thing I can do is that I can first look at the collection of the features at the beginning. So for this one, I have 1, 1, 1, 2, 2, 3. So this is a multi-set of all the features in my graph. Okay? And I look at it, so this is for G. And for H, right now, if I connect them, I get the same. So I cannot really tell whether this is the same. So then I proceed. But when you proceed, what you do is that in the next layer, for every node, your new feature will be basically the collection of features, the multi-set of features from your neighbors together with your first feature. Okay, so for example, for this node, my new feature will be 3, which is my own feature from the previous iteration, and also the multi-set feature of my neighbors, which is 1, 1, 2. So this node now has this as my feature representation. Now if you look at this node, my new feature is 3, but then my neighbor has 2, 2, 1, which is different. So now your feature is they're no longer the same collection of features. So at this step, you say these two graphs are not isomorphic. Okay, because if they are isomorphic at every stage, they have to generate exactly identical feature set. So you proceed with n iteration, this is then terminates, it will converge. Then if you cannot tell at that point still, you just say, I don't know. Otherwise, at any moment, the features that are not the same, you say they're not, the two graphs are not isomorphic. Okay, so this ultimately is an almost a linear time iteration. It's a very simple procedure to address the graph isomorphism problem. Yes? There's no starting point. You're using the collection of the all nodes feature at this point, so it's a multi-set. There's no node that's
of the 3 here are not the same, but maybe there's another 3.
Oh yeah, so you're right. So I shouldn't just say because of this, I know this are not the same. I should now look at the new collection of all those features and not the same. Thank you. Yeah. So, but in this case, we'll see that these two new sets are not the same. Yeah. Thanks. So if you just limit this to a simple graph, really what we're doing is that for a given graph, now I generate this new representation for this graph. In particular, this new representation is that at the beginning, my initial node feature is just whatever you supply me the attributes. Okay. Then when I iterate n iterations, and at every iteration, I update my feature by taking myself and my neighbors sets. Okay. So at any k, you have for every k, you would have a collection of the current node feature. That is the representation of your entire graph. Okay. And given two graphs, each graph has a collection of features across n steps, n layers, so same for H. If for any k, these two collection of node features are not the same, you return they are not isomorphic. Otherwise, you say we cannot tell they might be isomorphic. Okay, so this is the same as what I just said, but now I'm just limiting this to a graph representation for each individual graph. Okay, so each individual graph now, we're basically using the sets as across n layers to represent. All right, and it's easy to see the similarity between this WL test and this method passing architecture I just mentioned. Because here in the method passing, instead of maintaining this multi-set, I'm simply aggregating them through the super function. Okay, so we can map them to some fixed dimensional space instead of keep maintaining this multi-sets. Okay, and indeed, you can show this is a very informal statement. You can show that they express in terms of differentiating graphs. Method passing graph learning, no matter how you parameterize it, have the same power as the WL test. So what that means is that if you have two graphs that WL test cannot tell them apart, then no matter how you parameterize the method passing neural networks, they cannot, the output is two graphs will be the same. So they cannot tell them apart as well. The image will be the same. Okay, but if two graphs can be differentiated through the WL test, then there exists some method passing neural network whose output, whose image will be different as well. Okay, so this is just very informal statement. There's actually a series of the original work limit themselves to very specific type of node features, but then later they follow-up work to generalize this. Okay. All right, now, so the implication of this result in terms of this expressiveness through WL is that actually the MPNNs, their capacity depends very strongly on the initial node features. So if you imagine that I have some oracle, for every node, I simply encode the isomorphic type of this graph, then I can tell them apart. Okay, so it really depends very strongly on the initial node feature. But in practice, of course, you cannot afford to do such things. So very often, your initial node feature is something, let's say, degree, or depends on the wiring neighborhood. And when you use such initial node feature, then MPNN cannot compute simple quantities. It cannot differentiate, for example, all irregular graphs. If you use degree as the initial node feature, it cannot compute cycles, shortest cycles, or the number of cycles in the graph, and so on. Okay, so that's a limitation of the MPNN. So there are ways that people try to help to alleviate this problem. And one way is that instead using the so-called higher order graph neural networks, I consider not just me and my neighbors, but consider multiple interactions with multiple nodes. Okay, and this also this is where there's a lot of ideas also come into picture. There's also the so-called method passing simplicial or cellular neural networks, where you are starting from graph, you create a certain simplicial complex or cellular complex, and then perform method passing over there. And as you mentioned, that combinatorial class for hot class for simplicial complex, there also is being used to design those high order neural networks. So let me actually now come to our work. Now, so I said that the MPNNs from expressiveness as expressed as WL tests. How about how about universal approximation? Okay, so intuitively, can MPN approximate all continuous functions defined on the space of graphs? Okay, say from the space of graphs to, let's say, a scalar, a real vector. Okay. Now, to answer such a question, we have to have a topology on the space of graphs. Okay, and how you define that, you have to be a little careful. Okay, and one easy way to induce the topology is that however you put a metric structure on the space, and then that will induce a topology. Okay, and you might think that okay, when you have graph distance, we have graph added distance, we have metric graph, we also have this house distance, and so on. Okay, but actually, I would like to argue that added distance is not the right metric here. The reason is because we already know that I'm going to collapse a lot of graphs whose added distance could be arbitrarily large, but I'm going to collapse them into a single point because I cannot differentiate them. Okay, so the question is that what could be a suitable metric or pseudo metric, in fact, because I'm going to collapse distances. So this is what I want to introduce. So this is what together with Chen, Lim, Molly, Taiwan, we basically introduced the so-called WL distance. So essentially the idea, intuition coming from the WL test that I just told you. Okay, so this is a pseudo distance on the space of graphs. Okay, and it has a nice property that this is essentially compatible with the WL tests, namely the two graph has distance 0, it only if WL test cannot tell them apart. Okay, and also you can argue that as a possible neural network is universal, it possible continuous functions where the continuity is induced by the pseudo distance. Okay. I'll only give you a very high-level intuition of this WL distance in the interest of time, but let me also point out that after then trying to understand universal transmission of broad neural networks, this WL distance has additional motivation because in general we know that standard graph distance like added distance and so on, this is often energy partial compute and also hard to approximate as well. This say constant factor can be hard to approximate. Okay. And also in practice, very often your graph is extremely much just a pure combinatorial structure. Very often our input is a combinatorial graph together with no features, the attributes. Okay, so when you compare them, you want to take that into account as well. And the WL test can handle the attribute graph because it takes attributes as input. But right now the problem is that WL test only give you yes or no with the same or not. It's not a distance measure. So intuitively, we want to kind of extend this WL test into a distance. And the idea is that if you look at this WL representation that I introduced earlier, at every level K, it essentially is using multi-set of features to represent a node. Okay, and then to see whether to have the same node, you just test whether this multi-sets are identical or not. If I want to compare them, I want to give a distance. So I essentially kind of want to give a distance to those multi-sets. So the idea is that if we can kind of metrize those multi-sets, then I will have a way to give a distance to the graph as well. And this is achieved by, essentially, instead of multi-set, but we use the language measure to represent the multi-set. And when we, through the iterations, when I aggregate features of my neighbors to get a different multi-sets, so this essentially is replaced by using the push forward of measures. Okay, push forward map induced by some function. Okay, and now as I keep aggregating through the layers my neighbor's feature, I essentially in the WL test I get multi-sets as my feature information. Okay, now in this new language, we're going to basically have what I call the hierarchy of probability measures, some measure space. Okay, and finally to compare them, then naturally we use the optimal transport to compare those probability measures as up to finally give us a distance measure. Okay, so that's the intuition. All right. So now, as I said, I will not get into details, but very briefly the terms that I mentioned. And to have this measure language, we'll view the graph as a Markov chain, which is very natural. Markov model and graphs, the graph has a natural connection. So the example here, so assume every node has some feature, which is in some metric space. And you can think that instead of view this as this graph, you can think that this is basically every node associated with the Markov kernel, which I have probability Q to stay at this node itself. And the transition probability is basically this probability Q, I stay here, and then with some probability 1 minus Q, I will move to one of my neighbor, and I treat them equal. So each of neighbor receive minus Q over distance divided by 2 out of Okay, so every node now is associated with the measure, which is this Markov kernel. Okay, so that's this is just a more normal way of defining that. And I call this a Z-labeled measure Markov chain. So here the label is not like a a labeled graph where you know the correspondence. Now here the label just means every node is associated with a node feature, and this node feature is from a metric space Z. So for example, Z can be RD, okay, but it can be other metric space as well. Okay, so a graph now is represented by this the labeled measurement of chain L, M, and C. And as I said, that the way that we're going to perform the aggregation is through the push-forward map, because at every iteration, I need to aggregate feature from the neighbors. So what is this push-forward map? So let's say you have two spaces, X and Y, and you have a map psi between them. Okay, so this would induce actually a push-forward map on the space of measures from X to the space of measures on Y, defined so that if you give any measure on X, say alpha, so alpha is any measure on X, then this would, but mapped to another measure on Y, where essentially for every little region E on Y, you simply look at the pre-image on X and then sum up all the collect all the measures there. Okay, so it's like that you're reweighting your measure, this mass, you're reweighting through this measure defined on F. Oh, sorry, this measure defined on X. Okay. And the widest distance here is already mentioned yesterday. We talked about persistent diagram, so I will skip the notation here. But essentially, it's just a way to compare measures. Here, I'm using measures defined on the same space, but they don't have to be defined on the same space. Okay. All right. And as we continue to perform this push-forward maps, you're actually going to, at the beginning, you have a metric space Z, and then after the push-forward, you're going to now get a measure on the space of Z. But then as we continue to do this push-forward, ultimately, you're going to have the probability measure on the space of probability measure over Z and so on. So this is going to accumulate. So space is becoming more and more complex at this point. Okay, it's going to be the space of the measures defined on the space of measures over the, and so on after K times over Z. Okay, so it's a mouthful, but ultimately this helps us to formally define this WL distance. Okay, and you don't try to read this. I will give you a quick example in a minute. Let me just point out that what you're having is that at the beginning, you are going to label every point, every node in your graph to some metric space, mapped to some metric space Z. Okay. Then at the first iteration, you're basically going to use, so this labeling function right now is a map from the graph nodes to metric space D. Okay, and as a result, this have a push forward induce push forward map on the space of measures. In particular, now I can apply the push forward of this for every node X graph node. I can apply the push forward map to the measure, which is the Markov kernel at that node. Okay, this will give me a measure on Z. This would be my new feature at this point X. And then you repeat this process as you go up. Okay. And at any moment, you will have a collection of all these measures. Essentially, it's like the collection of the node features to represent your graph. And we compare to graph at this level using the largest time distance between the measure at that moment. Okay, so I'm skipping a lot of details, but this is the idea. So what exactly is this giving us? I mean, here's a super simple example. Let's say that in this graph, I'm just initially using my labeling function. It's just a degree of each node. So at the beginning, at the 0 stage, the feature at, oops, I'm using L0, this notation here. So for example, the feature at A is just the 2, it's my degree is 2, but the feature at B is 3. Okay, now, what is the feature at the level 1? Well, let's consider the node A. Okay, so I have this labeling function going from the node of the graph to this case. In this case, it's just the real value. Okay, and now at A, I simply look at the push forward of this applied to the Markov kernel at A. The Markov kernel at A, let's say that the probability of staying is 0, and it's just was probability 1/2, I would go to B, was probability 1/2, is the probability distribution over all the nodes, which essentially is 1/2 here, 1/2 here, and 0 everywhere else. Okay, so in other words, after this push forward, I basically, the feature at A is the push forward of this, which is simply that now I map this to the real value. I look at, okay, for this value 1/2 in the real value, this representation, I have 2 nodes giving me that value. Okay, so essentially, we'll see that, oops, I'm sorry. So this is the feature 3, this is feature 2. So basically, my image is that I have 1/2 of my measure will be at value 2, and 1/2 of my measure will be at value 3. Okay, but if you consider, let's say, this E, okay, if you look at what is the push forward of the probability measure here, I have 3 neighbors. The 2 of them have degree 2, 1 of them is degree 1. So the push forward will be that 1/3 of the mass will have value 1, and 2/3, which is the sum of these 2 measure, will have value 2. So that's the representation of my neighbor. So essentially, it's like a histogram of the features from my neighbor weighted by this Markov parametric node. Okay. And as they continue, it becomes more complicated. All right, but with all of this definition, it's still very well behaved, nice mathematical construct. So you can show that this indeed is a pseudometric, and indeed it is compatible with WL test, namely it's 0, even though maybe WL test cannot tell them apart. And you may be curious, because it sounds so complicated that measures of the space of measures of the Z, but actually we compute this using essentially almost a standard probability procedure bottom up in this time. And the bottleneck is really to do the optimal transport. So you can use approximation algorithm for optimal transport. You can improve the space. Okay, so it can be computed, and we have computed using this just as a way to directly using the pseudometric as a way to classify graphs. And well, but of course that what I mentioned really see that is that the universal approximation and this promised. Now you can precisely quantify that k-layer method passing graph neural network will be universal approximation for the continuous function on the space of graphs where the topology is induced by this level kW distance. Okay, so it's kind of what we hope to achieve. So I'm running out of time. Maybe actually just very quickly tell you this more recent result. This is very interesting about the expressiveness for graph transformer, which prior to this work, there's not much understanding of what's their capacity really is. Now, remember that we have 2 ways to add to inject the sum graph information into the transformer. One is using this absolute position encoding by putting all the encoded graph information at the nodes. The second one is that I'm going to use a matrix D to weight the self-attention, the RP, the relative position encoding. So the first observation is very simple. It's done already in previous work, and the proof is just coming easily from the computation hypervariance of the transformer. It's basically that the APE transformer is actually no more expressive from the differential graph perspective than just the initial set of position encodings. Okay, so your initial collection of node features cannot tell 2 graphs apart. No matter what you do in your transformer, then you still cannot tell them apart. Of course, that by doing transformer, you may add you may make the distance more meaningful, you get a better feature representation, but from the differential graph perspective, it's no more powerful than the initial collection of node features. Okay. So what this says is that if you are going to use your architecture, you are going to use APE, you really have to make this initial node position encoding very, very strong. Okay. Now, how about the RPE? And it turned out that for RPE, I couldn't directly just use the WL test because it's a little, it's ill suited for that. Okay. However, you can modify this WL test into a weighted version, which is weighted by this N by N matrix, N by N relative position encoding. Okay. So in particular, when I collect my feature from the neighbor, you also collect for each of the neighbor, you also take this the pairwise relation between that into account. Okay, so this is a generalization of the standard. This is even more powerful than the standard of one that we have. If you choose this position encoding correct, and and it turned out that this RP transformer is as strong as the this weighted version of the WL. In other words, if two graphs cannot be differentiated by this weighted WL test, then they cannot be differentiated by any RPE transformer. Okay, I realize that I didn't have the other direction, the converse direction also holds. Okay, all right, and this again have some of the horror of this is that if you, of course, the question is how you design this initial relative position encoding. Okay, it turned out that we use some of the common choices like graph, adjacency matrix, Laplace matrix, random walk matrices, and so on. Then the resulting RP transformer is as expressive as the standard. Is at least, sorry, as expressive as the standard that one that we have. It can be more powerful. Okay, so in other words, if you just use adjacency as part of our relative position encoding, you already get some of that, at least one that we have. Okay. All right, and now, interestingly, it sounds like the APE is less powerful than RPE, but interestingly, it all lies in that how we design the initial position encoding, either for the smooth one or for the pairwise one. So it turned out that given any APE, okay, given any absolute position encoding, there actually exists a universal a function f such that a function which works on two node features. So you give me two node feature and return one single value feature. Okay, so no matter what absolute position encoding you give me, which is a node feature, if you use this function, you can get this function basically between u and v. Now using this function, I can get now a new value for any pair of the nodes in v. Okay, because f works on the product of the features from u and from v. And it turned out that this RPE is as expressive as the initial APE. Okay, so in other words, I have a function f such that given any APE, I can convert that into an RPE, which is equally expressive. Okay, and this function f is continuous, which means that you can approximate this using neural networks using the MLP. And in other words, this also implies that if I want to have an APE over some specific position encoding, I actually don't have to do that. I can just first transform those features into an RPE and then run an RPE transformer on top of that. Okay, this is as expressive as the APE. And the other way also goes, namely, if you give me any RPE, it turned out that there's a way to map this RPE to an APE such that the resulting APE is equally expressive. Okay. Now, there's a difference though, which is that the way that I'm going to map this RPE to APE actually depends on the input graph and the input RPE. It's not a universal ending. Okay. While in the previous case, you have an F that works for all pairs of graphs. Okay. Here, depends on input graph, this map might be different. So even though you know such a map exists, but this result is less useful in practice. You cannot really convert this to, because this G changes as you change the graph. Okay. But and anyway, so this also have an interesting practical implications. Maybe let me just skip that. Maybe the bottom line is that on the surface, it sounds like the RP and APE can be made equally powerful. It depends on how you supply the initial position to the initial features. Okay, But if you read deeper into the results, APE, the power is much harder to design the right feature for APE. So in practice, it suggests that it's much easier to use RPE as relative position encoding. Okay, so I'd be happy to talk to you more about this if you're interested. Now, I was hoping to also talk about some of the ways to mitigate some of this limitation. And I'm running out of time. Maybe just let me tell you that one of the couple of things. So as we said that depending on the initial node feature, MPN cannot encode a lot of information like cycles, number of components, and so on. Okay. So one way to mitigate that is that we just add a stronger initial position to capture those before we gather the massive passing neural network. Okay. And the natural way to do that, given that this is a topology crowd, is that how about that I use the persistent homology to summarize the local graph motif at every node and use that to supply to the massive passing graph neural network. So we call this persistent enhanced graph neural network. Okay. So basically, it's your node persistence. So let me skip that. But basically, for every node, I take a certain neighborhood of this node as the local graph motifs around it. And then I put a suitable filter function on that. Let's say the shortest path distance to the base point. And then you summarize that using the persistent diagram. Okay. And the persistent diagram actually of the simple shortest path distance encodes quite a bit of information, including the clustering coefficients, the number of edges going from layer K to layer K plus 1, and so on. And we cover all this information from the persistent diagram of the shortest path distance function. Okay, so now this persistent signature capture information that's hard for massive passing neural network to capture. So use this to augment the massive passing neural network. So this is a very simple way by just put a 1 plus 1 to 2 type of way to use topology. Okay. And now, as I mentioned earlier, that people are using some visual complexes and cellular complexes induced from graph and perform neural networks, massive passing neural on top of that. Okay. So I want to raise the open question here is that what's interesting is that you can do all of it. In fact, there has been a lot of work and there are different ways to lift the graph to some visual complex. What's lacking is theoretical understanding to articulate exactly by doing this, what you are achieving and what extra expressiveness power you are obtaining. Okay. People tend to use the same WL test that I mentioned earlier for this task as well, but that's ill-suited because the WL test, just by nature, is very different from the type of information that the topology is capturing. So when you use this language, you're not getting much. Okay, so I think it's really interesting to think what could be the right language to model this representation power that's more suitable for this kind of topology enhanced neural networks. Okay, so we have to chat the interesting offline. And I mentioned there's also this oversquashing problem. Let me just point out that the way we relate to this oversquashing behavior was the effective resistance while we were up. Okay, and use that to help to mitigate this as well. And then skip the last point. And hopefully to give you one example on the chip design application where I put many of these ideas together to have a practically very effective architecture. And then skip that. And just come to my conclusion slide. And so basically here, this is some of the recent exploration we have done. I hope that this conveys the point that from your network. I mean, first, this is very versatile. This is extremely powerful for so many applications, molecular biology, or social networks, or kind of low and high dimensional point cloud data. You can all convert them by some representation graphs or simple complexes. Okay, so to have effective learning architecture on them is extremely useful and very be applied to many applications. But as I said, the theoretical understanding, which I really touched upon the representation power, but in general, this is very limited understanding over there. Okay, there are many other questions, especially the high order models. What is the right language to describe the power of high order models? And how do you balance trade-off the representation power and the computation complexity? Because when you go high order, the computation complexity increases exponentially as well. Okay, and And also topology to logical and geometrical help us understanding the interpretability of the results in learning models. That's what help us describing the generalization of models and so on. There are many interesting questions. Hopefully, I can attract a few of you to work on that as well. Thank you.
So thank you for the wonderful talk. Are there any questions? We have time for just a few brief questions.
Hi. Beyond the complex computation of the specific features, I got a question because basically what you were mentioning, right, is that we could find a better way to find features of the graph. Beyond the specific algorithm, is there, as I create a more complex measure for these features, does this affect in any way, shape, or form the training process of the neural network? I'm having to some degree, yes, numbers at last, but perhaps more with more coding or more complex coding. Does this affect in any shape or form at the moment of training, or do they learn their tasks faster or slower?
Well, at the most simplest level, that if you are going to ultimately representing a feature using a finite dimensional vector, because that's what we do ultimately when we feed this to the so even with precision diagram, you can perform precision image or some other ways to vectorize it, right, to feed it into the as a node feature. So when you do that, ultimately from a training perspective, it really depends on the dimension of your feature. Okay. Now, but there are other questions, which is that by adding more feature, is it necessary? If you add a redundant feature and use this feature, is it necessary for the training? It's not clear, given that usually when you add use persistence, you probably have intuition that this is capturing cycles, whatever that could be useful for the application. So I also want to just mention that I mentioned some visual complex, but the Hodgkin class, for example, yesterday there are several talks on the harmonic class and so on. The kernel space, like the modeling the cycle space, the cycle space representation coming from the Hodgkin class has also been used as to supply this initial position encoding to augment the.
Thank you. So we will leave the rest of the questions for the break, and let's thank Yusu again